Cast a turbine blade with cooling passages inside it, and sand molds are out of the question. Miss 2 millimeters on a ship propeller, and the vessel burns extra fuel for a decade. Skip one refining step, and stainless steel cracks under load. Coming up, how giant foundries shape metal into the parts civilization runs on, plus the loop nobody talks about at the end. Everyone assumes a foundry is a place where metal gets hot and then metal gets poured. That description is not wrong, but it leaves out the part that actually decides whether the casting works or gets scrapped. A large foundry pours more iron in a single week than many entire countries produce in a year, and every pound of it has to leave the furnace at the right temperature, the right chemistry, and the right cleanliness. Gray iron, ductile iron, and compacted graphite iron each respond differently once they enter the mold, and each has only a narrow processing window for producing a sound casting. Miss the window, and you get a casting that looks fine on the outside and fails the moment somebody bolts it into a real machine. The furnaces do the melting. The metallurgists, the pouring simulations, the digital imaging, and the sensors do the harder work of making sure what leaves the ladle is what the drawing asked for. The casting is only as good as the liquid that made it, and the liquid is where most of the trouble starts. And that trouble starts inside the furnace, where the whole process is either put on the right track or begins to go wrong. Induction furnaces do the melting for most modern foundries, and the reason is simple. They heat the metal from the inside using electromagnetic fields rather than fire from outside. That gives foundries something they never had with old fuel-fired furnaces: actual control. A medium-frequency induction furnace can melt steel, iron, aluminum, copper, or brass. Each of those needs different temperature settings and different holding times, and mixing them up ruins the whole batch. Get the settings wrong once, and you have paid premium prices to produce very expensive scrap. The furnace itself is the easy part. What matters is how tightly the operator can hold the temperature, the chemistry, and the timing while thousands of pounds of scrap turn into liquid metal. Melting the metal is one thing. Cleaning it up afterwards is a whole different problem. Arc furnaces generate heat by throwing an electric arc between graphite electrodes and the scrap steel below, reaching temperatures over 3,000 degrees Fahrenheit. Once the scrap is liquid, the furnace becomes a refining vessel. Argon-oxygen decarburization, AOD, takes over from there. A mix of oxygen and argon is blown through the molten steel to burn off excess carbon and pull out dissolved gases. Skip AOD, and the steel comes out looking finished, but cracking under actual load. AOD is how stainless steel earns its corrosion resistance and its toughness in one shot. Before the furnace door ever opens, another supply chain has already been running in the background, the one that makes the mold materials. A foundry does not just melt metal, it also needs sand, and not the kind you find on a beach. Foundry sand has to be almost pure silica, washed clean of clay, dust, and organic material with a controlled grain size and a predictable shape. Sand that arrives dirty puts holes in the casting, ruins the surface, and traps gas that has nowhere to escape. Nobody talks about the sand supplier at a foundry, but if the sand is bad, nothing downstream can save the day. A wash plant scrubs raw silica through screens, water jets, and spiral concentrators to strip out the heavier minerals and rinse the fine particles away. Water gets recycled through settling ponds so the operation does not drain the local river. What comes out at the end is a stockpile of clean, sized silica ready to be bonded with clay and shaped into molds. The point is simple. A foundry that ignores the quality of its incoming materials is a foundry that spends most of its time explaining scrap rates. Clean metal and clean sand only get you to the starting line. The next challenge is the shape itself. The metal is ready. The next question is what shape it will become. And the answer starts with the mold, not the machine. Sand casting is the oldest method still in daily use, and there is a reason it refuses to go away. A pattern of the finished part gets pressed into bonded sand, the pattern is removed, and molten metal is poured into the cavity left behind. The tooling costs almost nothing compared to steel dies, which makes sand casting the only sane option for parts weighing anywhere from a pound to several tons. Sand casting is where you land when the part is too big, weird, and cheap to justify anything fancier. But sand casting is not just dumping metal into a hole in the ground. The mold has to be built with the same care as the pattern above it. Workers pack green sand into a wooden or metal flask, tamp it down evenly, and cut in the channels that let the metal flow and the air escape. Miss a vent and gas gets trapped inside the casting. Skip the risers and the metal shrinks as it cools, leaving voids nobody sees until the part fails on a test bench. Every hole and channel in the mold is there because somebody once made a casting without it and learned the hard way. The finished mold gets closed, clamped, and lined up with the pouring cup. Molten metal enters through the sprue, runs through the gating system, fills the cavity, and rises into the risers as a signal that the mold is full. From the outside, the pour looks about as complicated as filling a kettle. The complications all happen out of sight, inside the mold. Sand casting handles the big and the rough. When the geometry gets complicated, foundries reach for a completely different approach. Investment casting starts with a wax replica of the finished part, injected into an aluminum or steel die. The wax patterns get assembled onto a wax tree, then dipped repeatedly in a ceramic slurry and coated with fine sand. After 10 or so coats, a solid ceramic shell has grown around the wax. The wax is melted out in an autoclave and recycled, leaving a hollow shell. The shell is fired above 1000 degrees Celsius to burn out residues and gain strength. Only then does molten metal, sometimes as hot as 1680 degrees, get poured into the still hot ceramic. A sand mold cannot produce a turbine blade with cooling passages running through it. The geometry alone rules the method out. The shell breaks away, the parts come off the tree, and the finishing begins. The lost wax process gets its name from the obvious. The wax gets lost on purpose. Each shell dipping adds thickness, and the total number of coats depends on the size of the casting and the weight of the metal it will hold. Fewer coats and the shell cracks under thermal shock. Too many coats and the process becomes uneconomic. Foundries pour the metal while the shell is still hot, which lets the liquid metal flow into thin walls before it starts freezing. Once the shell is broken away, the real work is not finished. It has barely begun. Each cast part comes off the tree with feeder stubs still attached, and those have to be cut, ground, and inspected. Heat treatment adjusts the internal grain structure so the mechanical properties match the drawing. Tensile tests pull samples until they snap to confirm the alloy is what it claims to be. A casting can pass every visual check, and still fail the pull test because visual checks do not see what is happening between the grains. Radiographic and dye penetrant tests hunt for cracks and porosity the eye cannot catch. Only after that does the part get packed and shipped. Every one of those steps exists because somebody, somewhere, tried to skip it and paid for the lesson. Then there is the newer approach, which throws out the pattern entirely. A 3D printer builds the mold directly out of bonded sand, layer by layer, straight from a CAD file. No wooden pattern to store or machining time to wait for. Complex cores that would take weeks to hand build in a traditional pattern shop come out of the printer overnight. Loose sand gets brushed away and recycled. Up to 95% goes back into the next print. The mold moves straight from the printer to the pouring floor with no pattern shop step in between, which was unthinkable 20 years ago. Before the metal ever gets poured, most modern foundries run the whole thing in simulation. Software models the mold filling, tracks the cooling, and predicts exactly where microporosity will form. Cold shots, gas pockets, shrinkage voids, all mapped in colors before anyone touches a ladle. When the numbers get high and the alloy is non-ferrous, foundries switch to die casting, and everything about the process changes. Instead of pouring metal into a sand cavity, molten aluminum or zinc is injected into a steel die under thousands of pounds per square inch of pressure. Cycle times drop from hours to under a minute. The dies themselves are engineered pieces of equipment, cooled with internal water channels, opened and closed by machines that weigh as much as a small house. Closed-loop injection control adjusts pressure in real time as the metal fills the cavity. The dies cost a fortune and the parts cost pennies. That is the whole reason die casting exists. High-volume automotive parts, power tool housings, structural aluminum components, all of them come off die casting machines. And once the die casting machine is running, everything upstream has to keep up. The aluminum arrives as ingots and gets melted in induction furnaces at rates around 1.5 tons every 45 minutes. Molten metal is refined with argon, which is rotated through the bath to strip out dissolved gases and floating contamination. The purified aluminum is transferred to holding stations that keep it liquid until the machine is ready. A robot with gram-level precision then pulls the exact dose of metal through a pipette dipped below the surface. The metal never sees air on the way into the mold, which is the whole point. The alternative is pouring from a ladle into a filling chamber, which works for many jobs but always risks trapping oxide films on the way in. Once injected and pressed, the aluminum solidifies in seconds. X-ray inspection then checks whether the inside of the part matches the outside, because a cast part that looks perfect can hide voids nobody would find until the customer starts calling. Machining, trimming, and precision measurement follow, with tolerances checked down to 3 microns. Die casting works because everything downstream is automated to keep pace with the machine. Robots handle the hot parts. CNC machining lines pick up where the die leaves off. X-ray CT scanners hunt for internal defects. Universal testing machines pull samples until they break to confirm strength. What comes out at the end is a batch of parts identical enough that quality control has to work hard to find any variation at all. Iron foundries have their own answer to the volume problem, and it looks nothing like die casting. Automated tight flask molding machines churn out up to 38 molds per hour, each one built, closed, and delivered to the pouring station without a human touching the sand. Pattern changes take 60 to 90 seconds. You swap the plate, the machine adjusts, and production resumes. Setting chills and sleeves into the molds happens fast enough to keep pace with the rest of the line. Molten iron flows from the ladle into each mold in sequence, with a worker checking pouring temperature between cycles. The whole point is to make identical castings, one after another, without variation creeping in. Iron castings up to 250 pounds, brake rotors, gearbox housings, pump bodies, differential cases, come off these lines in numbers that keep entire industries supplied. Green sand molding lines take the same idea and run it in a continuous loop. Molds are formed, closed, poured, cooled, shaken out, and the sand goes right back to the front of the line to be mixed with fresh binder and formed again. The whole system runs on one cycle time, and every station has to match it. Slower stations create backups. Faster stations sit idle. The engineers who design these lines spend most of their time chasing balance. Then there is lost foam, a method that skips the wax and skips the wooden pattern. Polystyrene foam patterns are coated with a refractory wash, dried, and buried in loose sand inside a flask. A vibration table compacts the sand around the foam. Molten metal is poured directly onto the foam, which vaporizes on contact and gets replaced by the metal as it fills the cavity. The foam pattern stays in the mold and vanishes when the metal arrives, taking the parting line and the cores with it. Geometry that would keep a pattern shop busy for weeks comes out on the first pour. The trade-off is that every casting needs a fresh foam pattern, so lost foam works best for complex parts that would be miserable to make any other way. And then there is centrifugal casting, which uses spin to do what gravity cannot. Molten metal is poured into a rapidly rotating steel mold. Centrifugal force flings the liquid outward against the mold wall, forming a hollow cylinder as it solidifies. Impurities and lighter oxides are lighter than the metal, so they migrate inward and end up on the inside diameter, where they can be machined out and thrown away. What is left is a casting with unusually clean structure and higher mechanical strength than most gravity-poured methods can deliver. A bronze bushing has to be perfectly round and dense enough not to fail in service. Cast it wrong, and the problem shows up the day somebody actually installs it. Tubes, rings, bushings, sleeves, cylinder liners, the parts that need concentric geometry and dense grain structure come off centrifugal lines. But every method covered so far shares a hidden weakness, one that only shows up when the casting is scaled to something truly huge. All those methods exist for one reason: to make the parts that machines actually run on. And nothing pushes a foundry harder than a big propeller. A ship propeller is not just a shape, it is a piece of controlled hydrodynamics, cast from bronze ingots, sized anywhere from 300 millimeters to 2.6 meters in diameter, weighing sometimes tens of tons. Every blade angle, every leading edge curve, every taper is designed to move a specific vessel at a specific speed with a specific fuel burn. Get the geometry wrong by a few millimeters and the ship burns extra fuel for the rest of its service life. A blade that is off by 2 millimeters costs the operator more over 10 years than the propeller itself cost to make. Modern propeller foundries use patternless rapid prototyping. A computer program generates the blade shape from input data, and a CNC machine mills the pattern or mold directly. Induction furnaces melt the certified bronze ingots. Foundry crews use mold and casting techniques refined over decades. Every finished propeller is inspected on computer-controlled measuring machines that check the geometry point by point, because at this scale, eyeballing it is not an option. Casting a propeller is all about controlling geometry and gravity wins if you are not careful. The pattern begins as a block of EPS foam milled by a robotic arm into the exact shape of the propeller blade. Sand is packed around the foam pattern, then the mold is heated to burn out any moisture. Molten bronze, heated in a crucible until it glows almost white, is poured through the runners and into the mold cavity. Workers in reflective suits stand back because bronze at pouring temperature does not forgive careless handling. Once the metal cools, the sand mold gets broken apart with heavy weights to reveal the casting inside. Then the real work starts. CNC machining of the propeller hub, robotic grinding of each blade, and manual polishing by workers in protective suits. A blue fit test with marking compound confirms the propeller mates perfectly to the shaft. A propeller can weigh 20 tons and still need to match its shaft to within a fraction of a millimeter. Engine blocks push casting in a different direction entirely. An engine block is a labyrinth of oil galleries, water jackets, cylinder bores, and mounting bosses. Thin walls next to thick sections, all of it in one piece. Aluminum ingots are stacked and fed into furnaces, melted, and transferred to holding ladles. High-pressure die casting machines then inject the molten aluminum into steel dies. Some engine blocks go from liquid metal to finished shape in under 2 minutes, which is shorter than most factory lunch breaks. Robotic arms extract the hot casting, cleaners knock off the runners and flash, and inspectors check the surface for the slightest defect. What comes off the line is an engine block ready for boring, honing, and eventually a set of pistons. Millions of these are cast every year, and every single one has to be identical. Pump bodies live a hard life. A single defect in the casting and the whole assembly leaks under pressure. Pumps handle water, chemicals, sewage, and abrasive slurries, sometimes for decades of continuous service. The cast iron or bronze body has to hold pressure, resist erosion, and match the impeller inside with tight clearances. Foundries producing pump castings use induction melting, automatic pressure pouring, and shot blasting to finish the surface. Every casting is designed close to the final shape. Near-net casting reduces the amount of machining needed later. CED coating, applied electrochemically, protects the casting from corrosion before it ever leaves the plant. A pump that fails on installation costs everyone involved a bad week, so foundries treat pump castings like the safety-critical parts they actually are. Then there are wind turbine castings, which are simply enormous. A wind turbine hub is a solid casting of ductile iron, sometimes weighing 20 tons or more, and it has to hold the 3 blades against the loads generated by decades of wind. The hub sits at the top of a tower, higher than most buildings, spinning slowly through weather that would ground an airliner. There is no easy way to replace it. If the casting fails, a crane the size of an office building has to come out to swap it. Replacing a 20-ton hub sitting 100 meters up in the air is a full shutdown, involving a specialized crane that costs 6 figures a day. Spheroidal graphite cast iron gives the hub the combination of strength and vibration damping it needs. Foundries produce these castings in dedicated lines with heavy overhead cranes, since a 20-ton casting is not something you shove around with a forklift. Every hub gets ultrasonic inspection to hunt for internal voids, because the ones that fail in service almost always fail from a defect nobody caught at the factory. Structural steel nodes solve a problem that welding cannot. In a complex truss or a free-form building frame, several steel members converge at one point at odd angles. Welding all of them together on site is possible, but slow, expensive, and unreliable at the geometry involved. A cast steel node captures the entire junction in one piece, with tolerances tighter than any welded fabrication can achieve. The casting arrives at the site, the members bolt or weld into it, and the geometry works because it was designed to work, not because a welder in cold weather managed to hit the drawing. Cast nodes improve fatigue performance, stiffness, and overall structural resilience. Bridges, roof structures, and architectural landmarks now use them routinely. The casting process involves 3D modeling, finite element stress analysis, non-destructive examination, and full-scale destructive testing of samples. Every node has to prove it can carry the load before the real ones ship. One large steel casting can take weeks to make from start to finish. Documents get reviewed against nuclear industry standards, chemistry is verified with spectrometry, molten metal is poured at over 1,600 degrees Celsius into massive molds coated in refractory. After cooling, the casting is heat-treated in furnaces the size of small buildings, then machined to tolerances measured in fractions of a millimeter. Every step exists because the finished part will spend decades in service where failure is not survivable. Slag pots are the unglamorous heavyweights of the casting world. In steelmaking, a slag pot catches the molten slag that floats on top of liquid steel, the impurities, the flexes, and everything the process needs to remove. The pot has to survive repeated cycles of scalding slag, thermal shock, and the physical impact of tons of solid slag being dumped in and out. Traditional slag pots were cast by conventional methods and had short service lives, high scrap rates, and long production cycles. Modern designs use CAE simulation to model the pouring and cooling process before casting begins, which lets engineers spot shrinkage zones and hotspots in the software, rather than on the shop floor. The pot itself is a bowl-shaped container with lifting lugs on both sides and an internal grill that helps break up the slag flow. One large slag pot casting can weigh over 40 tons and still needs to stay dimensionally stable through repeated shock loading. Every improvement in slag pot casting extends its service life, cuts scrap costs, and keeps a steel mill running without interruption. The gains show up in the quarterly reports, not the daily headlines. Centrifugal casting scales up in ways that seem almost absurd until you see it. The largest centrifugal casting dies in the world can produce cylindrical castings up to 36 feet long and 5 feet in outside diameter. Moving those dies into position for pouring is an operation that requires overhead cranes, specialized heavy-duty transporters, and a floor rated for loads that would collapse most industrial buildings. Imagine a mold big enough to cast a pipe you could walk through. Now imagine spinning it fast enough to fling molten metal outward against its walls without the whole assembly tearing itself apart. Centrifugal castings at this scale serve defense, paper mills, and heavy process industries where seamless tubular geometry with dense grain structure is not optional. Success depends on three things: stable mold rotation, controlled temperature, and a carefully regulated pouring rate. Rolling mill rolls are another category where casting scale becomes a serious engineering problem. One mill roll can weigh tens of tons and has to spin under thousands of tons of pressure while metal is fed through it, thousands of times a day for years. The roll body is cast, then machined on lathes that dwarf anything you have seen in a normal machine shop. Foundry crews use double-poured or centrifugal techniques to create a hard, wear-resistant outer layer around a tougher ductile core. A roll that fails in service does not just stop the mill, it takes the whole rolling line down and everything upstream backs up until it is replaced. The casting has to be sound from the surface all the way through, since a hidden void near the working diameter will grow into a crack under load. Foundries producing rolls maintain their reputation on longevity. Rolls that last one production run longer than the competition are the ones that win the next contract. Spinner discs are small in size but enormous in importance. These investment castings, made from nickel and cobalt superalloys, are what turn molten glass into the fine fibers used for insulation. The disc spins at high speed while molten glass is fed onto it, and centrifugal force throws the glass out through thousands of tiny holes on the rim. Every hole has to survive the heat. A full foundry tour shows just how many disciplines converge in one building. Pattern shops with CNC milled wood and styropor patterns feed the molding lines. Induction furnaces charge two 6-ton units in parallel. Hand molding stations use whirl mixers to bond the sand. Cranes move ladles of molten iron. Grinding machines finish the raw castings. CNC machining centers turn them into finished parts. Every step is tied to every other step. The largest hand-mold foundries in the world produce castings that reshape entire industries: press platens, wind turbine components, energy conversion parts, raw material processing equipment. These are ductile iron castings weighing hundreds of tons apiece. One mold is built by hand from thousands of pieces of sand. Multiple ladles pour simultaneously to fill the mold before the metal starts to freeze. But everything covered so far assumed the metal was iron or steel. When industry needs something lighter, faster to cast, and better at conducting heat, the whole approach shifts. The whole aluminum story starts underground, in rocks nobody outside the industry has ever heard of. Bauxite is the raw ore, mined mostly in tropical regions. 4 tons of bauxite refine into 2 tons of alumina, which smelt into 1 ton of aluminum through the Hall-Héroult process. The math is punishing. Enormous amounts of ore for a modest amount of metal. Only after all of that does aluminum reach a foundry ready to be cast into something useful. Primary aluminum smelters are strange places, because they need almost as much electrical infrastructure as an entire city. A typical smelter runs pot rooms visible from space, with rows of electrolysis cells drawing enormous currents through a bath of molten cryolite and dissolved alumina. Pure aluminum sinks to the bottom of the cell and gets siphoned off periodically. Carbon anodes are consumed in the reaction and replaced regularly. To keep this running around the clock, some smelters were built next to their own dedicated hydroelectric plants, dam networks stretching across 90 miles of mountains, with tunnels carrying water between lakes. Building the tunnels took over 2,000 workers armed with manual calculations, slide rules, and no GPS. Nobody would sign off on doing it that way today. and that alone tells you how much these smelters depended on their own dedicated power. Once the aluminum is smelted, it flows into casting pans, where alloys are added to give the metal its final properties: strength, corrosion resistance, formability. From there, it heads downstream to rolling mills, extrusion presses, and foundries that turn it into sheet, wire, castings, and everything else. Aluminum never rusts and can be recycled endlessly, which is the only reason the numbers on primary smelting make any sense at all. Aluminum recycling is the reason primary smelting has not collapsed under its own energy costs. Melting recycled aluminum takes about 5% of the energy needed to make it from bauxite. A large industrial shredder can eat a 2,394-pound bale of aluminum siding and extrusion in under a minute, reducing it to fist-sized pieces ready for the furnace. Every foundry running aluminum blends fresh primary metal with recycled scrap in careful ratios because the chemistry has to end up in a narrow specification window. Bad scrap will slip into a good melt without warning, and the whole batch of castings comes out porous. Nobody wants that conversation with the customer. With the metal ready, the foundry side of the aluminum industry gets to work. Gravity casting into permanent steel molds, called concilia in Italian, is one of the oldest methods still in daily use for aluminum parts. The tooling is more expensive than sand molds, but far cheaper than die casting dies, which puts gravity casting in the middle ground where it does its best work. Aluminum ingots are melted. The molten metal is poured by hand or by robot into permanent molds, and the mold cavity fills under gravity alone. No pressure injection. The cast part cools inside the steel mold, which pulls heat away quickly and gives the aluminum a fine grain structure. Fine grain structure is what turns a decent-looking casting into a part that actually holds up under load. Simulation software models the metal flow before the first pour, so engineers can spot cold shuts and shrinkage voids before they show up in real castings. X-ray inspection catches internal defects after the fact, because aluminum porosity tends to show up exactly where the part cannot afford it. Aluminum gravity casting only works at production scale because of automation. 2 anthropomorphic robots handle the pouring cell, one loading molds, one pouring molten metal, while a human operator monitors the process from behind safety barriers. The molds cycle through the cell non-stop, one after another, at a pace no manual crew could keep. Melting furnaces feed molten aluminum to holding vessels that keep the metal at the right temperature until it is needed. A worker periodically skims dross from the surface because oxide films trapped in the melt can weaken the casting. The casting robots pour into multi-cavity molds that produce several parts per cycle. Automation does not just make aluminum foundries faster, it makes them safer, since molten aluminum splashes are one of the more unpleasant things that can happen in an industrial setting. Downstream, CNC machining centers finish the castings to final dimensions. Hardness testers, X-ray machines, and coordinate measuring machines verify that every part meets its specification. Design engineers work directly with customers in 3D CAD to develop the mold, and constant supervision follows the mold through every manufacturing step. Bronze plays a different role than aluminum in the foundry world. Bronze, an alloy of copper and tin, sometimes with lead, aluminum, or nickel added, earns its keep in applications where corrosion, wear, and marine environments would destroy most other metals. Bronze bushings turn under load for decades without seizing. Bronze propellers hold up in salt water, where steel would rust away. Bronze bells ring for centuries. But casting large bronze pieces is not something you do casually. A big bronze pour starts in an induction furnace, where copper and alloying elements are melted together at temperatures over 1,100 degrees Celsius. The molten bronze is transferred to a crucible, which glows almost white as workers move it toward the mold. Bronze at pouring temperature is heavy, hot, and unforgiving. One bad spill and the shift ends immediately. The sand mold is prepared with multiple sprues to fill large cavities evenly, since bronze cools fast and starts to freeze the moment it touches the mold walls. Pouring proceeds steadily until the risers show the mold is full. What comes out after cooling is a solid bronze part that will outlast the machine it is bolted into. Aluminum billets are the raw material that most downstream aluminum products start from. A billet is a solid cylinder of cast aluminum, typically several inches in diameter and anywhere from a few feet to over 20 feet long, ready to be fed into an extrusion press or a rolling mill. Producing them at industrial scale requires a specific casting method, direct chill casting, where molten aluminum flows continuously into a water-cooled mold and gets pulled downward as it solidifies. The mold shapes the diameter, the water cooling controls the solidification, and the length depends on how long the operator runs the pour. Each billet has to be free of internal cracks, cold shuts, and porosity, because every defect in the billet becomes a defect in whatever extrusion or rolled product comes next. A cracked billet fed into an extrusion die wrecks the die on the first stroke. That die costs 6 figures. Foundries producing billets run 24-hour shifts, with molten aluminum arriving from melting furnaces and finished billets being cut, marked, and stacked for shipment. Furnaces hold thousands of pounds of molten metal at a time. Every step is metered: flow rate, temperature, alloy composition, because the customers downstream have tolerances that leave zero room for improvisation. The billet casting line is a chain of specialized machines that operate as one continuous system. Gas-fired melting furnaces bring the aluminum up to pouring temperature. A degassing machine strips dissolved hydrogen out of the melt. Hydrogen porosity is one of the classic villains of aluminum casting, and if you skip degassing, you will find hydrogen bubbles trapped in every billet you make. Filter plates catch any solid inclusions before the metal enters the casting table. From there, molten aluminum flows through a launder into the casting molds. The billets form as the metal cools from the outside in, pulled downward at a controlled rate. A skimming process removes surface dross throughout the pour. When the billets reach full length, they're lifted out with a crane and moved to the automatic cutting machine. The cutting machine trims the ends and slices the billets to the exact length ordered, because customers pay for the length they specified, not the length the foundry happened to produce. Laser marking identifies each billet with its alloy, batch, and traceability data. From there, they head to trucks or rail cars for shipping. Cast aluminum billets travel further downstream than most people realize. Extruded aluminum profiles from billet get bolted together into formwork systems used to shape concrete on high-rise construction sites. Each formwork panel can be reused over 200 times, which spreads the original casting cost across hundreds of buildings. Sheet ingots, the flat cast slabs from the foundry, feed the rolling mills that make aluminum sheet. A cast slab enters the cold mill nearly a quarter-inch thick and leaves as coil measured in thousandths of an inch. Between passes, it is annealed to soften the metal for further reduction. A fresh casting looks nothing like the part on the drawing. It comes out of the mold with the gates still attached, the riser stumps sticking up, flash running along every parting line, and sand baked onto the surface. Somebody has to cut all of it off, grind it down, and hand over a piece that actually matches what the customer ordered. For decades, that somebody was a human being with a grinder and safety goggles. Robotic grinding cells have quietly taken over the worst of it. A 6-axis arm with a diamond wheel handles gate cutoff, flash removal, and surface grinding at a pace no human worker could keep up for more than a few days without an injury. Abrasive media life management tracks how worn the wheels are and swaps them before a bad grind ruins a good casting. Scrap rates drop, part yield goes up, and nobody has to breathe silica dust for a living anymore. Some inspections happen with cameras, others happen by pulling something until it breaks and writing down the number. A DNV-certified sling test lab does the latter with heavy steel wire ropes, the ones used to lift wind turbine blades, oil platform modules, and pieces of ship hulls too big to move any other way. The rope goes into a hydraulic testing rig the size of a small warehouse. Cables get tensioned to the certified working load, then to twice that, then to the point where the manufacturer would rather look away. At the control panel, an operator watches the load build while the rope is tested. Pass the test, and it is marked and cleared for delivery. If it does not hold, the certificate does not get stamped, and the manufacturer gets a very expensive conversation instead. Foundries producing large castings run the same logic on their test samples. Nobody wants to be the engineer explaining why a load-bearing casting failed without a paper trail. Sharpie impact tests, hardness tests, and chemistry checks stack on top of that. What ships with any serious casting is not just the part itself, there is a whole folder of test numbers riding with it. The problem with destructive testing is right there in the name. You cannot pull test the actual casting the customer paid for. Non-destructive testing is how foundries check the inside of a part without cutting it open. And there are half a dozen methods, each one hunting a different kind of defect. Magnetic particle inspection works only on ferromagnetic materials. A magnetic field is applied to the casting, then fine iron particles suspended in ink or fluorescent liquid are dusted onto the surface. Wherever there's a crack or a discontinuity, the magnetic flux leaks and drags the particles into the flaw. Under UV light, the crack lights up bright green against the dark surface. A defect nobody could see suddenly looks like it is drawn in highlighter. Liquid penetrant does the same job on non-magnetic materials. Apply a brightly colored liquid, wait for it to seep into any surface-breaking crack, wipe off the excess, and apply a chalky developer that pulls the penetrant back out. Cracks show up as sharp red lines against a white background. Radiography, X-rays through the casting onto film or a digital detector, hunts the interior. Denser regions block more radiation. Voids, porosity, and inclusions show up as darker or lighter patches on the image. Modern digital radiography lets inspectors zoom, enhance, and archive images that used to require a darkroom and a chemistry kit. Ultrasonic testing sends high-frequency sound waves into the casting and listens for echoes. Any internal discontinuity bounces the sound back, and the return time tells the inspector how deep the flaw sits. Phased array systems steer the ultrasonic beam electronically, mapping large sections of a weld or a casting in one pass. Eddy current testing uses induced electrical currents to find surface and near-surface cracks in conductive materials. Thermography spots hot and cold anomalies with an infrared camera. Every method has its niche. No one method catches everything. High-volume foundries have taken the same idea and pointed it at castings. An inspection conveyor moves parts past cameras, laser scanners, and X-ray stations at a steady pace, one after another, with no operator required to pick up each piece. Vision systems flag surface defects. Laser scanners check dimensions against a CAD reference. Anything that fails gets diverted into a reject bin without slowing the line. 10 years ago, somebody with a caliper stood at that conveyor for 8 hours a shift. Now a camera does the same work at 3 times the pace, with zero fatigue. But the castings that fail inspection do not just disappear, they go somewhere. And where they go turns out to be one of the most interesting corners of the industry. Every casting that fails inspection has to go somewhere. It does not go into a landfill. It goes right back to the front of the line. Watch an aluminum casting foundry run through a full production cycle and the loop becomes obvious. Aluminum ingots get charged into the melting furnace. A degassing rod bubbles argon through the melt to strip out dissolved hydrogen. Modification and refinement adjust the alloy chemistry, magnesium, silicon, copper, until it matches the specification for whatever hydraulic pump body or engine housing is being cast that shift. Test samples are milled from the melt and analyzed on a spectrometer that spits out concentrations of a dozen elements in seconds. Chemistry has to hit before anything gets poured. Low-pressure casting machines fill steel molds with molten aluminum pushed up from below under controlled pressure, slower than die casting, cleaner than gravity casting, and better for structural parts that need to hold pressure. The upside is beautiful castings. The downside is a machine bigger than most people's houses that requires a dedicated maintenance crew. Each casting then heads to X-ray inspection. Anything with internal voids or porosity that exceeds spec gets rejected on the spot. Hardness testers, helium leak detectors, and dimensional checks catch anything else. Rejected castings do not become waste. They get cut, sorted, and sent straight back into the melting furnace with the next batch of fresh ingots. The metal that failed to become a pump body will get another chance to become one on the following shift. But foundry scrap is only one stream feeding the recycling network. Everything else metal in the industrial world eventually shows up at a scrapyard. Old refrigerators, bicycles, I-beams from demolished buildings, aluminum siding stripped off houses. All of it gets weighed at the truck scale, inspected for hazardous materials, and routed to whichever line handles that grade. Ferrous goes to the shredder. Non-ferrous goes to the separation system, where 3 size grades pass over eddy currents that flick the metal one way and the non-metal contaminants the other. The scrapyard is a volume business. Everything else about the operation follows from that one fact. What comes out at the end is sorted feedstock ready for the mill or the foundry, tracked from point of arrival to point of sale. A full scrap metal recycling plant looks like a foundry that runs the process backwards, then forwards again. Aluminum scrap arrives in trucks. Extrusions, castings, siding, old wheels, whatever the buyer's network has aggregated that week. A mobile vibratory charging machine with a 4-ton capacity loads the scrap into the tilt rotary furnace. 15 tons of oxy-fuel-fired capacity brings the load up to melting temperature, and the rotary motion keeps the bath mixed while the scrap turns into liquid metal. Contamination, plastic, paint, oil, other alloys, burns off in the flames and gets captured by the emissions control system. The molten aluminum transfers to a 15-ton holding furnace with a porous plug for gas injection, which is where the chemistry gets adjusted before casting. Argon or nitrogen bubbles up through the plug, dragging dissolved hydrogen and oxide inclusions out of the melt. Skip this step, and every ingot cast from that furnace will have hydrogen porosity baked into it. and every downstream buyer will start asking uncomfortable questions. The molten metal then flows onto a 220-mold ingot casting machine. Each mold gets filled in sequence as the wheel rotates. Indirect water cooling solidifies the ingots as they travel around the loop, and by the time each mold reaches the demold station, the ingot inside is solid, hot, and ready to drop onto the conveyor. A robotic arm at the end of the line picks up the ingots and stacks them into bundles, 6 across, 12 deep, however the customer wants them. Cooling quench water hisses off the surfaces. Continuous emissions monitoring tracks what leaves the stack, and every particulate reading gets logged for the regulators. The finished bundle of ingots weighs a couple of tons and represents anywhere from 10 to 100 old refrigerators, depending on the day. From here, it heads to another foundry, another mill, another product, and the whole cycle starts over. Some scrap does not fit through the shredder because some scrap is a 14-ton steel ingot, massive castings that failed final inspection, oversized mill rejects, or heavy industrial pieces that arrived intact at the scrapyard have to be reduced before they can be recycled. A powder-cutting torch handles what an oxy-fuel flame alone cannot. The torch injects iron powder into the cutting stream, and the powder ignites in the oxygen jet at temperatures beyond what a standard flame produces. The result is a cut through solid steel. Sparks the size of tennis balls launch sideways. The ingot splits into manageable sections that can now go into the shredder. And this cycle runs in every country with a steel mill and a truck. Scrap yards from Chicago to Perth do the same job: receive, sort, process, ship, feeding recycled metal back into the supply chain that keeps foundries running. Every casting that fails, every gate cut off a good one, every worn-out machine part eventually returns to the melt. Whatever shape the metal was in yesterday does not matter today. All that matters is that a furnace somewhere is running. And that is the loop that ties the whole industry together. Every casting we have followed, from the first ingot charged into a furnace, through the mold, out the shakeout, past the grinders and the X-rays, into inspection, into service, eventually finds its way back to the front of the line. Scrap yards feed the melters, and the melters feed the casters that supply everything from bridges to ships to power plants. The material never really goes away, it only gets reshaped. What's the largest casting you've ever seen in person? A ship propeller? A turbine hub? A V12 engine block? Share with us. We'd love to hear your answer. Thanks for watching. If this run through the Foundry world was worth your time, hit subscribe. We are just getting started on the industries nobody explains properly. Take care.